So the first couple of questions have to do with quantum numbers. Now, for n equals 3, what are the values of L are allowed? N is the principal energy level, whereas L denotes which orbital we're talking about, either S, P, D, or F. So for n equals 3, our only possible L values are going to be from 0 to n minus 1, meaning from 0 to 2. And this is a range, not just 0 or 2. It means 0, 1, or 2. This is for L. If you want to go a step further, for ML, so this is our answer. If we want to go a step further, we can see that for each L value, ML has a possible value of negative L to positive L. Now, since for L is 0, there's only one possible ML. For L is 1, there is 3. There is negative 1, 0, and plus 1. And then for L equals 2, there is 5. So it's negative 2, negative 1, 0, plus 1, plus 2. I know that's sloppy, but whatever. And if you notice, these correspond to our electron configuration based on our orbitals, right? Because this ML and this L equals 0 corresponds to an S orbital. And this S orbital can only have 2 possible electrons, which are denoted by the opposite spinning electrons in the fourth quantum number, ms, which could either be, in every single case, plus 1 or minus 1. So in every orbital, you can only have 2 electrons, and they are positive and negatively spinning in order to have them come together or be happy together. Now, for L equals 1, that corresponds to a p orbital. And look, there's 3 orbitals within a p, and they correspond to 6, or maximum of 6 total electrons, if we were to break them into plus and minus 1/2 each. And then L equals 2 corresponds to our d orbital, which then has 5 orbitals inside, or 5 subshells, which can each hold a maximum of 2 electrons. So this should all make sense and correspond to electron configuration. The next question. Match the 4D subshell with the correct allowed combination of N, L, ML, and MS. Now, for 4D, it already tells you a lot of information. It tells you that N is equal to 4, so that's a definite. It tells you that L is equal to, what did we just say for D? D means that L is equal to 2, so we know that L is equal to 2. For L equals to 2, then our possible values of ML, like we wrote up here, are negative 2, negative 1, 0, plus 1, and plus 2. And our possible MS values are just simply plus and minus 1/2. So this is for a total of 10 possible electrons. Now that's not just true for 4D, it's true for any d orbital, 3D, 5D, or 6D as well, that they can have a total of 10 electrons at their maximum. Moving on, the photoelectric effect. So this is difficult for a lot of students to conceptualize, but I want to break it down for you. So using questions. Now we have the photoelectric effect for a certain alloy has a threshold energy of 5.56 times 10 to the 14 joules. This means that that is the energy required to kick off an electron. So now we could use our energy of a photon equation, which is E equals NH nu, which is the wavelength. And we need to use our speed of light formula to figure out the wavelength and the frequency, which is C equals lambda nu. And the first equation, our nu is our frequency, right, in seconds, and 1 over seconds. Our H, Planck's constant, is 6.626 times 10 to the negative 34. N is the number of photons, which in this case it's 1. So now we're going to write down our energy, which is our threshold energy level, and we need to figure out the frequency associated with that energy level. N is equal to 1. Our Planck's constant is 6.626 times 10 to the negative 34. And we're looking for frequency. So once we solve for this, by dividing by Planck's constant, we get, no, not 6, 8.41 times 10 to the 19th hertz. So that's pretty high frequency. Now, to go to the wavelength, we would simply put that into our speed of light equation. So we can divide each side by the frequency to come up with C divided by frequency equals wavelength. Now we can do that. The C is equal to 3 times 10 to the 8th, and our frequency is 8.41 times 10 to the 19th. So our wavelength answer will be 3.56 times 10 to the negative 12 meters. So that is extremely small. So that's going to be, that's actually less, that's a picometer. That's 3.56 picometers. So that's extremely small. This would be extremely high energy. Okay, moving forward. So electrons are ejected from a sodium metal by any light that has a wavelength shorter than 544 nanometers. What is the kinetic energy of an electron in joules that is ejected from the sodium light by light with wavelength 234? Okay, so this goes into more of the photoelectric effect. The other one was just a preview. Now, for the photoelectric effect, the energy of the incident photon that is kicking off this electron has to be greater than the threshold frequency. So it has to, or sorry, it has to be greater than the threshold energy, lower than the threshold frequency, meaning it has to have enough energy to kick off the electron. And the energy that is remaining, because we know that the energy of the photon will be more than required, that remaining energy is converted to kinetic energy. So this means our E photon, I'll write it as E photon, is equal to our threshold energy. So, and we call that the binding energy. So we'll call that binding energy minus the kinetic energy, which of the electron that is kicked off. So the extra energy is converted to kinetic energy. So this question is telling us all of the information we need, but very convolutedly. So it's saying any light that has a wavelength shorter than 544 nanometers, it's saying that that is the wavelength mark of the threshold energy. But since we know all of the equations we just talked about, that E equals NH nu, and that C equals lambda nu, we can come up with our answer. So our wavelength would be 544 nanometers. And we're looking for our frequency here. We're going to take the frequency and then we're going to put it into the energy equation. Or what we can do is do that directly. So we can do C over lambda equals our frequency. And then we can put that frequency right into our energy equation to figure out the energy that is the binding energy, meaning the minimum energy required for the photon to kick off an electron or to eject an electron. So that would be, since it's only one electron, we assume it's one. It's going to be Planck's constant, 6.626 times 10 to the negative 34 times 3 times 10 to the 8th, which is meters per second, speed of light, divided by our wavelength, which is 544. And this is going to be in meters, so it's 544 times 10 to the negative 9th meters. And we can solve this, and we get 3.65 times 10 to the negative 19 joules. So this is our binding energy. So it's the energy minimum required for a photon to have in order to kick off an electron and give it some kinetic energy. So this would be binding energy. It would go right there. So now it's saying, what is the kinetic energy? So we're looking for this of an electron in joules ejected from sodium by light with a wavelength of 234. So basically, we can solve the same exact energy equation, but with 235. With 235, this would be the energy of the incident photon that will be kicking off our electron with this amount of binding energy and some. That sum gets converted to kinetic energy. So let's do that. So our E photon would be equal to 6.626, 10 to the negative 34, same exact equation, divided by, instead of 544, it'll be 235 times 10 to the negative 9 meters. And our answer is 8.46 times 10 to the negative 19 joules. Okay. So what we can do is plug in everything we know. Our energy of our photon is 8.46 times 10 to the negative 19 equals our binding energy, which is 3.65 times 10 to the negative 19. And the energy of the photon should always be greater than the binding energy. If it's not, that means not enough energy is there to eject that electron, or it could mean you probably did the formula wrong. There's going to be minus our kinetic energy. So to find our kinetic energy, we can subtract, and then we could divide. Or really, we could just subtract. And we come up with 4.81 times 10 to the negative 19 as our kinetic energy in joules. Okay, so that's how you do that. All right, next one and the last one. What is the wavelength in nanometers of a line in the spectrum of hydrogen that arises from the transition of an electron from the orbital with n equals 5 to n equals 2? Now, this is the Bohr model. So it goes into when you input photons or energy into an atom, the electrons can jump energy level, and then they can come back down. This is called spontaneous electron emission. So the electrons, when they come back down and lose that energy, the remaining energy is emitted in the form of usually visible light. And this is the equation we use to calculate our energy associated with that transition. So what we can do is, since it's a transition from n equals 5 to n equals 2, we can put in our n equals 2 as our n final, and our n initial is going to be n equals 5. And here's the general equation, but we can modify it to have it involve a transition from one to the other. This constant is always going to be the same. Multiply it by, this is where it gets different. You have z squared over n final squared minus z squared over n initial squared. So we're doing basically final minus initial to figure out our change in energy level. And that has to be separated this way based on algebraic principles. Now, we know our z, since z represents the atomic number. Hydrogen is going to be atomic number 1. And usually these questions are given with very low atomic number orbital or elements, such as hydrogen and helium. So n equals, or z equals 1, excuse me. And then n, our n final is going to be n equals 2. And our n initial is going to be n equals 5, because it's going from the 5 to the 2. So you can imagine this whole value, whatever we get here, has to be a negative number, because energy is being released. So the energy gained is a negative. So always think about that in context of the problem. So negative 2.178 times 10 to the negative 18 times 1 squared, or just 1 over 4, minus 1 over 25. And our answer is negative 4.57 times 10 to the negative 19 joules. So that is the energy associated with this transition. Now the question is not done yet. It's asking for what is the wavelength of this energy. So we can use an equation we just used to figure out the energy associated, or the energy associated with a wavelength. So we can do that right here. So E equals H parentheses C over lambda, and we can write that over here again. So E equals H C over lambda to figure out our wavelength. So now our energy is going to be negative 4.57 times 10 to the negative 19 joules equals Planck's constant, which is 6.626 times 10 to the negative 34 times our speed of light, 3 times 10 to the 8, over our wavelength, which is unknown. And we can solve for this, and we get for a wavelength 4.34 times 10 to the negative 7 meters, which corresponds to 434 nanometers. So that makes sense. That's in the visible light spectrum. That's kind of lower. That is violet. That's exactly violet, actually, for the hydrogen emission spectrum. So even with a little bit of rounding in there, we got the spot on the right answer. And if you notice, this is a negative number. Your answer would be negative wavelength. But we know that the wavelength always has to be positive. Even though this energy is being lost in the transition, it's still the energy of the photon that's being emitted. So we have to put that into account, take that into account, and make this positive. So feel free to like and subscribe to the channel for more practice problem videos like this one, and be sure to ask questions in the comments if you have any.